Hello everybody, welcome to this week's lecture. We have the 12th of July 2023. I'll hold a short recap of what we did in the past two lectures. As to some degree they're connected because the power devices, you're designing an amplifier which is supposed to amplify your input signal and deliver you an output power, and that output power you obviously want to transmit in some way or shape. In this case, we're in the RF world. We're operating at gigahertz levels at higher frequencies, so we usually transfer it towards an antenna, and that antenna radiates it out into the free space. Keyword antenna. We talked 2 lectures ago about antennas. We saw that there are multiple variants from them. To the left, there's an example of one of such a cascade antenna, and then a UMTS antenna integrated inside a iPhone 4 or iPhone 5. Different shapes and different forms all do the same thing principally. They enable the transfer of conductor-bound EM waves towards free space. Usually when there's an interrupt, the interrupt can be free space, the interrupt can be an open line, the interrupt can be something like an expander of this antenna here. We went through different types. We said that there's simple types such as just wires, a dipole, which also had this dependency on what frequency of radiation it had, dependent on the length of the interrupts, and the positioning of the interrupts also affected the way it radiated. We had then antennas that were further on used excessively in the past, in the military as well, horn antennas, conical horn, rectangular horn waveguides. Nowadays also used it intensively in labs to characterize more sophisticated, let's say, antennas which are integrated into chips, and into these chips you have both the antenna integration and the power device integration, the device that then drives this antenna. That's why from time to time you'll even hear the description as active antenna. That basically means an antenna which has an active power driver as its source. We then discussed more modernized concepts. These have been concepts that have existed for the past 30 to 40 odd years of patch antennas, which then use a dielectric substrate to generate a certain mode, to generate fringing fields and surface currents, and by introducing an interrupt or an edge length of lambda half, you will be able to then have a certain mode of radiation at a certain frequency point. Adding more of these patch antennas together, you form an array, and these arrays then, due to additive layering of the radiated waves, constructive interference, they dependent on the distancing from each other, they can create a singular radiation pattern, and also help in expanding the aperture, which means that the aperture becomes bigger, your focusing or your directivity becomes more narrower and higher. You can reach larger distances. For that, you can use also cascade antennas, as seen here, or you can use also a lens. Later on, we'll show examples. As I mentioned, all depends on this interrupt, the length of the interrupt, and how the current always moves back and forth. And with every move back and forth, a certain electrical length is seen, and once a certain electrical length is seen, a certain radiation pattern can be achieved. Important things to remember from the antennas were the antenna parameters, and these how an antenna plot looks like for a far-field plot. Antenna parameters such as the directivity. An antenna doesn't just radiate out in all forms and shapes, it radiates in a certain direction. You try to also have what you want your antenna to do is just not chaotically radiate anywhere, but to radiate at a certain point and try to focus the energy radiated at that certain point. This ability to focus that energy, let's say, is called the directivity of the antenna, that is taken with respect to an isotropic radiator, so a radiator which radiates in all directions equally. If you take then the directivity of that and the efficiency of that antenna, basically an antenna is not an active device. You cannot, as we've seen later, we discussed about active devices, we had a certain GM, transconductance. We had a certain input signal. That input signal was amplified by that certain GM. The GM is defined where our gate source voltage lies, where our drain source voltage lies, where our drain current lies. So it's a combination of the biases of the GM of the active device itself, and then we have an amplification. An antenna is nothing like that. An antenna is a piece of metal. It's a conductor. It has losses. And so the gain in the sense is the ability of this antenna to accumulate this radiated EM waves at a certain direction whilst taking into account also the losses or the efficiency of that antenna into account. And usually, ideally, efficiencies go up to 70% at most, and lay in the region of 50% around for example, for patch antennas, for patch antenna applications. Obviously, horn antennas have a higher efficiency. Antenna efficiency, the radiated power over the input power. The input power is the power that gets driven by the amplifier, by the power device. We have also mentioned that power devices have this thing called, we see power devices as two-port structures. So they have an input and output waves, and waves that are incident to the input, waves that are outwards from the input, waves that are incident in the output, and waves that go outwards. The output, they can be voltage waves. These voltage waves, when squared, will give you the power waves, and with the power waves you can define the spectral parameters and so forth. These waves that come in, they need to see a certain match. You're matching with a complex conjugate to be able to transfer most of the energy towards the next medium. In order to transfer this energy, you have to have a good input matching of the antenna, and that's why it's very relevant how much your antenna accepts energy and how much it radiates energy, and that part of the radiation is dependent on how many losses it has in the summary. This is the plot. As I said, this is an important. These parameters, directivity, gain, aperture, are important for the exam. The plot here, the 2D plot of what does it say? Well, in the radial axis, you have the definition of the angles. So how much your beam width is, your 3dB beam width. Your main beam is where your antenna focuses most of your radiation. Obviously, there's going to be other radiation that goes beyond your main beam. How wide this beam is, that's the 3dB beam width. That's also very important to know at what point the radiated power drops by 50%, by half. Then you have your side lobe level. So basically, I'm wanting to radiate in this direction, but sadly my antenna radiates also part of my energy into this direction, and then I measure how much dB difference does this have. That's called the side lobe level. This is called a side lobe when I'm radiating not in my main direction. And usually you want to have these side lobe levels 10 dB less or more, because you want your whole energy to be focused, because this energy is coming from your power device. Your power device is getting hot. You're trying to have you're having a large drain source voltage over it because you want a lot of power through your antenna, because you want to reach far places. So you have a lot of power. You try to match your antenna as best as possible to get that power from your power device to your antenna, and then you want your antenna as directive as possible to shoot it as far as possible. In the horizontal axis, you have the amount in dB, how much the relative to an isotropic radiator. The gain or the directivity, whatever you plot in this diagram. You can plot the gain, you can plot the directivity in this diagram, you can plot the realized gain, which takes also into account how much loss over the conductor you have, and so forth. But usually in this lecture, gain and directivity can be plotted there. Lateral resolution, the optical aperture, as I said, increasing the amount of components, spreading them wide. You can artificially increase the aperture of the antenna, causing your antenna to have a more focused gain or more focused directivity. As you can see, an antenna can be also represented by a simple circuit. This part is not that relevant for the exam, that's why we'll be moving on. Modern antenna design is, as we see here, it is designed always in combination with an amplifier. The amplified part is the part doesn't have this radiation approximation, whatever this drawing radiation dot on top of it. And you can really imagine modern circuits are really like that. They have the active RF components, and on the active RF components, that determination and you have radiation. Either you have an E-probe, which is then used to couple waveguide modes into a split block. So you have one amplifier only, but you have also E-probes to be able to get that energy out into a waveguide, and then from that waveguide into a waveguide medium, or the air with by a horn antenna again, or you have something like that, which is an on-chip antenna. Because this is a good thing about the on-chip antennas, is that then you can align a lot of them next to each other, and by these small chips, you can design a whole wafer where you align these to each other and span a huge aperture, have a very large antenna at very high operating frequencies. We saw an example of one such on-chip antenna, and how the problem was the higher frequency you go, the more free space path loss you'll have, the more losses you have from the energy in free space, and the more the less at all you will be able to produce sufficient enough power from your power device to drive your antenna, to drive the signal. So you want to increase the directivity, and many examples of increasing the directivity, adding vertical structures on the antennas and so forth. One of them is the lens. We mentioned in the beginning, lenses have been used till for forever, if one thinks about it. And in this case, there still remain usage in them in these modern devices for increasing the directivity, increasing the gain of the system. Modern antenna design, as is the modern circuit design anywhere, is done by using EM simulators, 3D EM simulators. We saw an example of that when I showed you a bit of CST and I showed you a bit of ADS, combination of how to use ADS and CST. You begin in ADS, you design, you have a schematic, you design components with predefined model definitions. You use a lumped definition of a capacitor, of whatever the case, to make an RC network, to make a matching network for your amplifier. That one then you lay out. Laying out means you take what you've done in schematic mode and you try to transfer it into a real life setting with transmission lines, with capacitors that are contacted via whatever. And you transfer that into a simulation medium, into 3D EM simulation medium, where you try to solve all these Maxwell's equations for certain conditions, certain specified conditions in materials, and see how the EM waves travel throughout the device. You have a source, you have a sink, and usually the sink is then the environment, is a perfect electric conductor defined, and you see how this, in ideal case, how the propagation of the M waves will be throughout your structure. We saw that with that you can design circuits that are very close to each other, with in terms of measurement and simulation, which is a good indicator. We also discussed about the multiplication law, of the fact that a whole system of arrays can be reconstructed by taking the performance of a singular element and measuring it with the function of the matrix, function of the, not the matrix, but of the system. And what is the function of the system in this case? It is the number of components, it is the distance of the components, and it is the orientation of the components. In this case, you can see such an example here, trying to increase the aperture by having multiple, instead of having a large dish, having multiple small dishes in equally distance positions, and a specific coverage, so that you can span this aperture. Similar here, a 3D rendering of what would be done, what is done in Chile. And similar concepts are used also in space and so forth, and in ZA, but that is not very the application of these modern antennas, of why we move into arrays, not only the aperture but also the ability to have MIMO, multiple input, multiple output. What does MIMO mean? Well, instead of having a 64 array construct so that you try to reach as many people as possible, you have 8x8 constructs, and these 8x8 constructs can always be superimposed into each other, so that you can span a virtual array, more cost-effective. A virtual array allows you to then steer the beam to directions, to people that require more bandwidth, whilst others receive it from traditional 3G, 4G UMTS transmitters, their base band supply. We'll check in because we have a small jump from here to power devices then. This part was all covered by Professor Kwai with the epitaxial layers, with respective components, with processing, etching, and so forth, doping. And we will move to I believe it's close by here. Yeah, this is where we then continued our second lecture. Why was this interesting towards this lecture? Well, in these devices where you see here, there's not just antennas in there, but there's also power devices in there, amplifiers and so forth. So there's amplifiers integrated with antennas, integrated in array settings. So it all connects in this way. And these amplifiers are very important because when trying to have new telecommunication standards, all of the baseband, all of the up to 5-6 gigahertz is very crowded, and all of the bands are used for something. And if you want to have higher bands, you have to go into higher modulation schemes. And having higher modulation schemes requires higher complexer modems, require complexer chips at some degree in your phones, and at some point you also reach the limit at how many COM points you can distinguish in an eye diagram or whatever the case it is, and thus, you need raw bandwidth more. At some point, modulation will not help you. You need raw bandwidth, and in order to increase that raw bandwidth, every time you hear new 4G, 6G, 5G, 7G, whatever the Gs will come, it will always be some higher frequency point where larger bandwidth is covered. And they are moving higher at higher frequencies. You know all the amplifier curves, the FT and Fmax, as we discussed last time, the maximum current gain FT and the maximum unilateral gain of Fmax, maximum power gain, they all tend to go downwards with their increasing frequency. And at some point you have them all at unity, which is you won't have any gain. An amplifier will not amplify to infinity. A horn antenna will transmit any frequency from a lower cutoff upwards, but an antenna it won't be able to transmit anything if the power amplifier doesn't generate the signal for it. And a power amplifier obviously acts as a bandpass as well, meaning that even if you have a source that theoretically could supply you with a low powered signal for higher frequencies, if the power amplifier itself reaches its FT, then or its Fmax, then you will not be able to send any signal out. And thus, power devices are very important. Reachability and higher, because we all want to use more data. We all want to have our life easier. We all want everything to be optimized. Everything to be optimized needs a lot of frequency. Everything to see everything high definition and good quality to view a match that is happening in the other side of the world live here, because your family is there, your relatives are there, to see them every day, to talk to them. It all requires bandwidth, it all requires space, and you are moving. We want to have that co-integrate into our life. That's why higher bandwidths are required. And in this case, antenna design and power amplifier design comes with each other. Power amplifier design, high voltages and high currents. As we said, we will apply high voltage. High currents will flow through there in order to have a high output power. We mentioned that there's limitations in that we have high electric fields that are across the drain gate contact, and those high electric fields can have a pinch off at some point, can generate heat. You can generate heat in the device, making the environment warmer and hotter, and things like that start to become problematic. Managing your heat, how do you set up, distribute the heat, how do you simulate it initially to even start with, to have a good foresight. The good thing about power devices is that they have a good carrier mobility and low ohmic contact resistance. The substrates are made such that they have a good thermal conductivity, like silicon carbide, for example, that is usually used as a carrier substrate for example, for GaN transistors, because it is a good heat spreader It has a heat coefficient similar to silicon, for example. We discussed some types of the semiconductor devices, both vertical devices, BJTs, and horizontal devices. FETs, MHEMTs, for example, have been shown. HEMTs or MHEMTs from GAS have been shown in the past few slides. And in this case, I think we then discuss about what the benefit of having what is even making it a power device? Why is it even able to sustain these high voltages? Well, because of the large band gap. In a band gap of above 1.12 electron volts was so band gap which goes, I think, above, not 1.12, but above 1.4 electron volts is already considered a large band gap. That's, I think, where gallium arsenide sits at, but other components such as GaN and silicon carbide have much higher band gaps and can sustain much higher drain voltages and thus also drain currents. We discussed that these are made in these like power bars. So these power devices are these fingers that are designed in this feeding structure, in this ghetto structure, parallel to each other, a gate, a drain, and a source. And you're parallelizing it. You're increasing, because in this case it's a HEM device. You're increasing the gate length, the gate width. The gate length is in this direction. The gate width. You're increasing the gate width, you're parallelizing it in order to increase the amount of output power you can sustain. So you're making a lot of these parallel transistor fingers. In this feeding structure, in this concealment of the gain, source, and drain, these are then packaged in these small metal alloy packages for heat transfer, mainly for heat transfer, and then are like inside the packaging you have an example of pre-matching and output matching and so forth. And I think I showed you also in the last lecture, and you can see it in the video of the last lecture once that is uploaded, how this pre-matching is designed inside the package, that the CST EM simulator comes into use there as well, and that not only is that there is also application for CST now. Modern design of such power bars occurs. We saw this finger structure for feeding the source and the drain, and the gate, feeding the gate, and then the source and the drain to contact the respective powers. We saw an example of what you do when you try to have to take silicon-based technologies and try to adapt them for higher output powers. This was this uniform doping with pre-doped areas in the added dope, not increased doping, but with increased layers, increased areas in doping inside the underneath the channel. And we saw that this on top of it, this shielding that occurs, and this added layers of doping, these added layers of doping, the LDD1 and LDD2, what they do is they allow you to homogenize the electric field that is underneath the gate drain contact, and the shield is also another factor that allows you to have more control over your gate, whilst having more control over your channel, whilst having a high voltage input, high voltage applied to it. The high voltage causes the higher electric fields, denser electric field, which can cause a pinch off, which can cause a burn of the structure to burn. And in order to avoid that, we try to add these added doping layers to extend the drain, and the shielding to be able to have more control over the carriers underneath. Also, another example of that, we talked about the fact that an important, as we said beforehand, we're trying to design, in the end of the day, we're trying to design a device that amplifies a signal, and that device should shoot that signal towards something you would likely like it to come to your phones. Thus, it comes through the base station. The base station has high power amplifiers implemented in them. The signal goes through other components of the transmission network that we'll see hopefully in this lecture as well. But they end up at the power amplifier. The power amplifier drives its power into the antenna. In order to drive the power into the antenna, the power amplifier load has to be matched to the input of the antenna, a complex conjugation matching. And even before that, antenna amplifier. Before that, you have the power that is driven into your amplifier, and that is also has to be matched to the input. So your amplifier has to be accepting that. It's a two-port device. It has to be willing to accept that, and a low amount of has to be reflected back. And in order to do that, you have a Smith chart. I believe you've seen a Smith chart beforehand, where you're plotting the complex impedance points that can be seen, and you have constant inductive lines and constant capacitive lines, where your where your resistance remains the same, but your complex or the imaginary part differs in terms of how much inductive and how much capacitive components you'll have. In the center is a reference impedance. In the center is always a reference point, a reference impedance, and then to the left and to the right. To the left you have your 0 point, to the right you have your infinity, and open circuit or short circuit, and then you transfer your impedances, move along the Smith chart according to what frequency point you operate and according to what device you have. And because we have, that's another example of a heat distribution for power devices. Yeah, you can take it at 10, you can take it at 1,000, whatever the system you're operating in. It's usually 50 ohm is taken because 50 ohm is the standardized norm of what everybody agreed upon to be the medium where we operate. Where if you buy a component from producer A, if you buy a component from producer B, and the component from producer A is a mixer, and you want this mixer to attach to your amplifier, and you put them together, you want them to be at the same match to the same impedance, and usually people agreed to that it should be 50 ohm. I think it was also 75 ohm at some point, and 50 ohm has also a reason why it is, because other aspects for us, for an engineer, it's an agreed upon requirement, and we match to that specific impedance. In this case, I think it's written there, whatever, it's written 10, but it can be 50 ohm, it can be whatever. The 10 is there because, yeah, the 10 is there because, as I said before in the lectures, in the prior lecture, not too prior, these power devices have a low input impedance when operating at the high frequencies. So we saw that at the low frequencies they have near infinity at the input, and then it moves lower around the capacitive part to the upside. And then I think I'll go to that page if I can hopefully find it. Yeah, here. That the input and output impedance, the input and output reflection coefficients, so the ratio between what is the reflection coefficient is the ratio between the incident and the reflected wave from the input, the incident reflected wave from the output. We can see that the output impedance is finite at some point, doesn't go to short circuit, but as long as the frequency increases, and here it is drawn kind of not intuitive, because the start of the frequency is to the right, and then the stop is to the right. It means that we move from 25 megahertz to 250 megahertz to 50 gigahertz. As we move along the Smith chart, we're moving towards lower impedance points, and we see that the input matching goes to the lower impedance points. And that's why in the other graph, the 10 was selected, because we wanted to just have, you can imagine here, if you're here with a reference of 50, and there is 10, now what is that for a value? Is it 7.5? Is it 7? Is it 6? It's not very easy to distinguish by the eye. So if you know that your impedance points will anyway lie in that region, then you take a reference which is closer to that region, and the reference is in the middle, and you have a higher span of values that you can then more exact say, oh, that is at 7.4, the other one is a 7.3, and so forth. But again, this is also, for the exam, this is one that is asked often enough to draw how the input and output reflection coefficients of such a device move along the Smith chart with frequency, and maybe an explanation that, hey, there is a high input impedance at the higher frequencies, and then the low input impedance at the operating frequency at 50 gigahertz, and so forth. Yeah, move a little bit back, because we discussed this, the power semiconductors, we can no longer stick with silicon. Silicon has a small band gap. The small band gap, what does it cause? We cannot apply high drain source voltages. Drain source or drain source in that case, but emitter collector bias, and due to that fact that you cannot span large electric fields in the device because you might have a device that just burns out, we need a larger band gap. And in order to have a larger band gap, we take combinations of these predefined semiconducting material, semiconductor materials to form base for with an option with a higher band gap, which is like silicon carbide or GaN or aluminum nitride, gallium nitride, aluminum nitride, and silicon carbide, and usually also indium phosphide and gallium arsenide is used. But you can see that the more we move with a higher band gap, the more we lose in carrier mobility. And what is the point in carrier mobility? Carrier mobility, we talked about FT and Fmax, maximum current gain, maximum unilateral gain, or maximum power gain. And these become in frequency. If I was as a frequency chart and this is 0 and this is 10 terahertz or whatever, or 1 terahertz in this case, it means that my gain reaches the point 0 at far sooner than it would if I have a higher mobility. But having a higher band gap means that you will have more power, which means that you can make a compromise. Hey, I'm not designing with GaN, I'm not designing a circuit that works at 1 terahertz. I'm designing a circuit that works at 5 gigahertz. And that circuit, when it works at 5 gigahertz, I can apply 40 volts at the drain source. Whereas for a gas device, I cannot apply 40 volts. I have to apply 4 volts maybe. So there's a major difference in the output power that can occur. And the operating point, frequency point, what you select in technologies. Silicon carbide also has the benefit of having a thermal conductivity of copper. That is the benefits also of these materials as well. Not only that, and some good to know facts about having, because of the band gap, they're in this property that they have see-through substrates, but this is all just in how the spontaneous and piezoelectric polarization happens in between and the creation of the 2-DEG layer. These are good things to know, and they're important to know for how these functions and operate, but won't be significant addition to the exam. I think, what did we want to say with? Yeah, this is also part of this how that there's always there's a gate contact, there's drain contacts. These drain contacts have an ohmic contact. They have a certain passivation because your gate is supposed to, and a certain current, in a certain barrier layer that is grown, so that your carriers in the 2-DEG layer in your channel don't tunnel through the gate. You want your gate to only control to control the carriers, but not to draw them towards the gate. And you don't have a doping in this case, but you just have a certain alignment of different bandgap materials, and the alignment of different bandgap materials twists your valence and your conduction bands so that you have points in the material in these bandgap transitions that you generate carriers, you diffuse carriers, and these carriers are polarized with spontaneous and piezoelectric polarization, and these polarization cause that there's certain orientations of the carriers occurs, and there in between these two layers a channel occurs, a channel which can allow the fast transfer of carriers. When looking at the comparison between a p-hemmed from GaN and a GaN hemmed, because of the amount of voltage that can be applied, the same says 1 volt in 1 volt steps increase how much voltage you can apply to the GaN transistor and how much voltage you can apply to a GaN transistor. You can see that the respective drain source current is also quite limited in the GaN case, and that's why your output power will be also limited. This is for one frequency point. Depends on what frequency point you're operating with, basically. Power devices aren't really done At 1 terahertz, you don't do power devices. You try to do low noise amplifiers, and you reach the higher power by having diode multipliers. And at some point, you use optics, lasers, and so forth to have the required or tunneling amplifiers. So these large Röhrenverstärker, not semiconductor devices that are mounted. But for lower frequencies, 20, 30, 100 gigahertz, 200 gigahertz, 300 gigahertz, you do have power amplifiers that are semiconductor based. And for these cases, you can see that having something with a higher band gap allows you to apply higher voltage, and applying higher voltage means higher power. And higher power means more money for you as a designer. It means more money for the company. It means more reachability, more information for the consumer, and so forth. Power means reachability. Reachability means having access to a lot of end users. Yeah, I think this is also an important part. We discussed some important parameters in this case, which was voltage amplification, current amplification, power amplification, the gain of the output power versus the input power, and then the transconductance, which is the rate of change of the output current with respect to the input voltage. We saw the matching of the Smith chart. We talked about FT and Fmax. I've mentioned it a few times here. Whereas maximum stable gain and maximum available gain. What does that mean, and how is that defined in terms of the K factor? The K factor was this special formulation that allowed us to define whether our device is unconditionally stable or not. And we can see, talked about the two-port device matching input and output. And the K factor was here, this line. If it is above 1, the device is unconditionally stable. If it is below 1, the device is not unconditionally stable. That does not mean that the device is unstable, but it does mean that if your device exceeds a gain of above the value where MSG is depicted, a maximum stable gain, then the chances of it being unstable are very high. So your device, and you design then if you take this device, you have this performance, somebody gives you this transistor, and you want to design at 1 gigahertz an amplifier, then you know that 1 gigahertz this device is not unconditionally stable, so you need a transformation network to make it stable, to go to the stable portions of your network. And you need to know that at this case, if you were to match this device for a gain of above 30 dB, you know that your device will start to ring. So you have a ringing oscillator. So you have a matching network which you try to move it to other operating points so that it has less gain, thus higher losses, but still operates stably. I think that will be also what we will discuss then after this case. Some formulations for yourself to later read. It is good to know these things, to know what the formulation for maximum stable gain is, what the maximum available gain, what is the formulation is for the K factor. That's also good how it is derived from the S parameters in this case. We can see it here. So I think we stopped here somewhere. Yeah. Now towards this part of the lecture, we have we're again confronted with. I think beforehand you probably were always confronted with voltage waves that enter the two-port circuit. And the topic of the two-port is always reoccurring because we're considering these devices as two-port devices to be able to then form formulations of why a certain amount of power needs to be driven in, a certain amount of power needs to be extracted from the circuit, how much gain it has at all, and what the performance of it is. And when we are usually observing these structures, these active components, power amplifiers, let's say, we're looking at them as these two-port devices. There's voltage waves coming in, voltage waves going out. And then if you take this voltage wave and you square it, absolute value of it with a reference impedance at 0, then you'll obviously have a power, the input power, the power incident into the network. If you take then the wave that's being reflected back, the B1, in this case, so A1 is what's going in, B1 is what is being reflected back. Why is it being reflected back? Because the source and the input of the two-port device don't have a matching impedance. Then you have the power that is the power that is power reflect from the input port of the network, or the power available from the Z0 minus the power that has been delivered